This is EN2041 Thermodynamics. Lecture 6. So in this lecture we're going to look at an introduction to gas power cycles, which means really what we're going to do is try to understand the nature of gas turbines and how gas turbines are fundamentally put together. I'll introduce a little bit in terms of how they're used and what they do. And we'll look at some of the thermodynamics in this introductory part. So this again is a flipped lecture, and what a flipped lecture means is you're going to watch this video. You're going to learn about all the material here in this approximately 1 hour session, and then after this session we'll come along to the lecture and we'll discuss the content of this video. And as I've said before, this is a much more effective way of learning. So we're going to have a quick look, just as before, how my lectures are structured. Is that in the first lecture we have a look at the technology, understand some of the terminologies, and then we go into the thermodynamics. We'll do a little bit more detail in this lecture. We'll actually look at some of the temperature entropy diagrams as an intro. So I may have mentioned it to you, is that my background is actually in gas turbines. So I've done a bit of research in gas turbines. I've done some testing. I've done testing at airports, and you'll see a video next where I kind of try to demonstrate the scale of a gas turbine in comparison perhaps to reciprocating engines. So we've done reciprocating engines in the previous 4 lectures. So let's look at gas power cycles, and what you'll notice is the scale is significantly larger with gas power cycles, and you'll see that can be quite a common theme in engineering, is that if you're trying to generate power on a certain fairly small scale, you usually go reciprocating engines, and then the next size range up from that is actually gas turbine power. So let's take a look at me trying to tell you something about gas turbines whilst there's 4 of them in the background running at quite a fair rate. Okay, just a bit of fun there. You can see that the engines are very, very loud. That's nowhere near full power. They were actually probably just idling in that particular case. It pretty much demonstrates that we're on a totally different power scale, and that's why it's useful for you to look at not only things like the diesel cycle, but also the cycles that we'll cover in this part of the module itself. So yeah, extremely loud, very, very powerful machines, as you can see, and used on a completely different scale with different applications as well. All right, so we've got some learning objectives for this particular lecture. Again, how learning objectives work is this is what you should be able to do or demonstrate once you finish the lecture. So first of all, you should be able to discuss some of the concepts of gas turbines, where and how they're used, and just some simple modes of operation. So we'll talk about either power generation or the provision of thrust. You should be able to demonstrate the temperature entropy and the pressure volume diagrams for the Brayton cycle. That's the cycle that we're going to look at in this particular lecture. It's also known as the Joule cycle sometimes, so let's not get confused between the dual cycle, which you've covered previously, and the Joule cycle, named after the thermodynamicist Joule, because most of the time we call it the Brayton cycle anyway, but it's just to give you an appreciation for different terminologies. And then the third thing is you will hopefully, but maybe this is a bit of an extension of the work, you'll be able to see how these systems will differ from vapor power cycles, such as steam power cycles, which would include the Rankine cycle as an example. You haven't done the Rankine cycle yet, but I know that in previous lectures or previous modules really on thermodynamics you would have touched on these things, so hopefully you'll be able to see the difference between the Brayton cycle and a vapor power cycle, for example the Rankine cycle. Okay, so these are the things that we're going to get at today's lecture. Let's get started with the introduction. All right, so by means of introduction, I'm going to show you another video. Now, this is on a little bit more of an extreme scale than what you've seen, which is me standing next to some civil engines, and they were simply just turning over at idle. Now, what I'd like you to understand in this is perhaps the difference between those 2 engines. So what you're going to see is an F100 engine, which is manufactured by Pratt & Whitney. Now, these are military jet engines. There's examples of military aircraft The F-15 has 2 of them, and the F-16 has 1 of them. This is a very, very high thrust-to-weight ratio engine. It's used for military applications, which means it's used to give very large amounts of thrust, so high speed, but it's also an afterburning engine, which means essentially the designers made this engine so that they could throw jet fuel into the exhaust, which will give it a huge kick up the backside, but not with a great amount of weight, because all they really need is a few pipes and just an afterburner assembly. So there's no real moving parts to an afterburner, and that's bolted onto the end of this engine. But this is a very high thrust design. So it's not really designed to be efficient. It's not designed to be quiet, and it's not designed for civil applications. It's what the original theme of the jet engine was when they were put together in the 1940s, which was just to give quite a large amount of thrust. So have a look at the statistics on the side before you look at the videos. This is an afterburning turbofan. When you see the scale of the power, it is quite surprising how figuratively how small this thing is. It's only 5 meters long. It's only a 1.2 meter diameter on the intake. So most people wouldn't be able to stand in the intake. It's too small. It only, and I'm going to use the words only carefully, but it only weighs about 1.7 metric tons. And if you look at the amount of thrust it gives for 1.7 metric tons, it's quite startling, this engine, the amount of power that comes out of it for its weight. So how much thrust does it actually give? Well, without the afterburner on, it gives about 80,000 newtons of thrust. And just to sort of make an analogy, that would be the equivalent of around about 8 metric tons. Okay, that's without the afterburner. When the afterburner is running, this engine gives out just over the equivalent of 13 tons of thrust, remembering that it doesn't even weigh 2 tons. So think of the power to weight ratio in this respect. We're not really comparing like with like, but it'll give you an idea for what these things are used for. So huge quantities of thrust. This is, relatively speaking, a fairly old engine. Actually, this engine was kind of designed in the 1970s and 1980s, whereas things have come a long way from now. And indeed, in more modern engines, they're actually lighter and they can burn hotter, and in many cases you'll get more thrust as well. But again, just have a look at what the engine is doing, how it's working, the different scales to what you might be used to seeing with reciprocating engines. Now, this particular film, I took it from YouTube, but it was taken in, I believe it's a military test facility in the United States, where what happens is they take the engines off the aircraft, they take them apart, put them back together again, service them, and then before they go back onto the engines, they'll put them on a test bed. And then the purpose of the test bed is just to run them up to 100% and make sure that they're working properly before they get put back in the aircraft. And I think what they've done on this particular case is quite rare. They've allowed some people to go into the test hall. You wouldn't normally do this because of the horrendous amount of noise generated by these things. So I think they've just done it for a bit of fun for some new recruits, but it certainly gives you an idea of the staggering scale you can get from an engine like this, which is operating on the Brayton cycle, which is what we're going to learn about in this lecture. So hopefully you got an idea for the amount of power that was being generated. If you were standing in that test hall, you would probably be terrified to the point of wanting to just get out of there and run away. I don't know if the video shows it. I mean, you can just hear white noise across your video speakers, but if you just were to imagine the magnitude of what's happening in there, it's quite something. So we're going to look at the materials contained within this lecture now. Previously, what we would have looked at is just reciprocating engines. And in reciprocating engines, we learn, whether it was in this module or whether you learned previously, that the cycle is split into into discrete operational phases, right? So there's 4 of these discrete phases. Each one is a non-flow process, and each one has relatively straightforward thermodynamics, which we can use to move between the different parts of the cycles. That's what we've learned. Now, we're going to do exactly the same thing for the Brayton cycle, but what we'll see is that as some of the heat addition processes are taking place, they're doing so under different conditions. So we take a slightly different methodology for the analysis. In a lot of cases for the reciprocating engines, the combustion or the heat addition is occurring at constant volume, and sometimes it's occurring at constant pressure. But for the Brayton cycle works because all of the heat addition is at constant pressure. That's the key thing. Now, this is something which is very much exemplified with gas turbines, because this is actually happening. Whereas with the reciprocating engines, it's very polytropic. There's things happening simultaneously because the piston is moving and changing the volume of the chamber. But with the gas turbine cycle, when heat is added, there's absolutely no change in pressure at all. So a lot of people have difficulty getting their head around that, because we're adding heat, we're causing the gases to expand, but the pressure isn't changing. And that's one of the unique features of a gas turbine, and that's one of the unique features of the Brayton cycle. So if you want to take away some key information from this lecture, one of the key things you need to learn is that in the Brayton cycle and in gas turbines, in the practical sense, heat addition occurs at constant pressure. Okay, let's keep going through the introduction. So this also differs from vapor power cycles, because the substance going through our turbine is always a gas, and that's why they're called gas turbines. Now, there's a lot of misnomer floating around in this particular area of thermodynamics, because quite often people think it's gas turbine because gas is the fuel. But that's not correct. It's a gas turbine because the working fluid is always a gas. Okay, so if you're having difficulty, remember that. Just think a wind turbine works with wind, and a gas turbine works with gas. It's always gas. Now that differs from a vapor power cycle, where it's a vapor going through the turbine. Now, vapor in our case implies that at room temperature conditions, so at 1 atmosphere, and let's pick an arbitrary number, at about 25 degrees C, the working fluid is actually a liquid. Okay, that's a vapor power cycle. We're not looking at vapor power cycles, we're looking at gas power cycles, okay, or gas turbines in this particular case. So in our case, the working fluid is always a gas. Now, yes, they're fueled on natural gas sometimes, but they're also fueled on liquid fuels like kerosene or aviation fuel, or in some cases you can actually put diesel fuel through these things. But that doesn't matter. What we're looking at is it's always a gaseous media going through the turbine itself. So the best example for us to study is the gas turbine. I think the best example for us to theoretically cover first is a jet engine, because we are more likely to have experience of a jet engine than of static power generating systems. And what I'll do is I'll introduce static power generating systems as we go through this lecture. But the first thing we're going to do is look at jet engines, propulsive jet engines, because you should have some experience of those. You've probably got more experience of reciprocating engines, because you can see when somebody might have opened up the bonnet of a car and you can have a look. Jet engines, very unlikely you've had a chance to have a play with one of those. However, you can see the application, you can see them working in everyday life. So we'll start looking at those in our preliminary studies. So if we were to look at a fairly simple system diagram, what this thermodynamic engine, what any thermodynamic engine does to a large extent, is shown in the following diagram. We take in air and we take in fuel, and we might take work through the process, we might take heat through the process. What any thermodynamic engine does is it makes a balance between work and heat. Sometimes it turns heat into work, sometimes it turns work into heat, sometimes it does a mixture of everything. But in the case of analysing and understanding our Brayton cycle, what we're going to say is our engine takes in air and fuel and it puts out combustion products, and it puts out work. It doesn't take any thermal energy in, that's going to come later on in the module when we look at things like heat pumps. So in our case, we convert chemical energy into work, just as we've looked previously with reciprocating engines. So there's nothing new about this diagram, but you need to just keep it in the back of your mind. This is what a gas power cycle does. So here is a gas turbine in the form that you're probably used to seeing it as a jet engine. So this has 4 discrete operational phases, just as we've seen previously with reciprocating engines. So what we have here is really 3 of those phases, and the 4th part is actually just the atmosphere sitting around it. But I'll go into that in a bit more detail later on. So what I want you to do is look at the diagram underneath, and we'll go through the different parts. So first of all, we've got the intake and the compression stage. Okay, so air flows into the intake and it comes across this compressor. So we call this part of the jet engine the compressor, and the compressor is rotating. Okay, so it's spinning around, and what's happening is it's squashing the air as the air comes through the engine. Now that compressor is being driven by a shaft, and the shaft is picking up work from the turbine, which is at the back end, but we won't worry about that for a short while. So as the air goes through, it comes up against the turbine blades. They're spinning and they're angled. So because they're spinning and they're angled, they're sucking the air in and they're squashing it. So if you look carefully at the diagram, you'll see that the cross-sectional area is becoming smaller and smaller. So the gases are getting squashed further and further and further as they go into the engine. Okay, and the reason that the gases are being drawn through is because they're coming up against angled blades, and these angled blades are being spun at a very, very high rate of rotation. So it could be well over 10,000 revolutions per minute, and they're squashing the gases down. Okay, so that's the compression phase. So almost think about this as if it was our reciprocating engine cycle. So we've had our induction and our compression. Okay. So then we move into the combustion part. So the air is now squashed. It's very hot because it's been compressed. So if it was perfect, it would be isentropic compression. So up goes the temperature just as before. And then we go into the chemical reactor part, which is the combustion chamber. Okay, so the fuel is mixed with the air. It's at high pressure and it's ignited and it burns. Now remember what we said is that the pressure doesn't change in the combustion chamber. The temperature goes up. Lots of heat release, but the pressure in this working section doesn't go up at all. Okay, it remains constant. If anything, it comes down a little bit because we have a little bit of drag as the air and the combustion process and the products go across the combustion chamber itself. So that bit in the middle that says combustion, that's the combustion chamber. So of course this differs from a reciprocating engine. These are discrete phases. They're not all in the same part, are they? The compression's done in a different part of the engine to the combustion. So that's different to a reciprocating engine. Okay, so we've got very hot gases now, and what we can do is we can expand these gases out the back of the engine. That's what we do. We expand them out the back of the engine, and then they go into the turbine section. So you should be able to see that there's what looks like 3 turbine stages in this particular engine. So they pick up energy from the gas. So they pick up and convert this thermal energy into work. And because they're allowing so again, we've got angled blades, but these are acting as turbines now. So they're picking up this thermal energy, they're turning it into work, and they're causing the shaft to rotate. And of course, that energy is being fed to the compressor. So the turbine drives the compressor, and the compressor is what's causing everything to go through. So if you think about it logically, what we've got here is energy being taken from the back of the engine and moved up to the front. So there's always a balance on how much energy you need between the front and the back, which we can look at in more detailed analysis later. So the energy that's left over, and there's a huge amount of it left over in this particular case, passes out the back of the engine, and that gives us thrust. Okay, and as you can see in the example of that F100 engine, that is a huge amount of thrust. So the thrust is coming from gases expanding. They're expanding because they're hot, and the heat energy came from the oxidation of the fuel in the combustion chamber. So that's the principle of the jet engine. It has discrete operational phases, exactly like the reciprocating engines that we've looked at. So we've got intake, compression, combustion and exhaust, but they happen across the engine, not all in the same place. And remember, the heat addition, the combustion, is at constant pressure. All right, what I'm going to do now is I'll show you a video on the next slide, and that video is really a solid model animation of. Right, so this part is the compressor, and that's squashing the air, and you can see there you go. It's linked to the turbine via the shaft, and the two of them are going to rotate together. Now, sitting around this is the combustion chamber. These are a series of cans in this particular case. The whole thing sits in a nacelle, and this nacelle should look familiar to you. So in comes the air, gets compressed. This is a radial flow compressor, but it's the same principle. The air gets squashed as it goes in, burns with the fuel in the combustion chamber. Then the hot gases expand out across the turbine. The turbine provides rotation to the compressor, and the whole thing generates thrust. So it all works together as one package. And that's pretty much the operation of a jet engine as I've described previously.
Okay, so I want to introduce a term now that will just help you to understand gas turbines a little better. It doesn't have a huge amount of relevance in terms of thermodynamic analysis of them, but it gives you an idea for typical gas turbine terminology. And this term is bypass ratio. And bypass ratio really gives us the understanding of the difference between what you might refer to as a military engine and a civil engine. So in the slide, there's diagrams of two engines. They're both manufactured by Rolls-Royce. The top one, the EJ200, is the engine that's used on the Eurofighter Typhoon, and then the bottom one is the Trent 1000, which is used on large civil aircraft. So I think that one's used in the Boeing 777, for example. And manufactured by the same company, but different parts of the same company. So the top one's manufactured in Bristol, and the bottom one is manufactured in Derby. But what I'm trying to get across in this slide is the difference in their designs and why the term bypass ratio is important. So let's look at the top example. The air goes into the front of the engine, as we've seen. It goes through the compressor, into the combustion chamber, and out through the turbine, and it provides thrust. Almost all of the air that goes into the front goes through the combustion chamber and across the turbine. So the exhaust from this engine is very hot and provides a lot of thrust directly. Its efficiency, and we're always careful with the word efficiency, so I'm going to use the term efficiency in a general sense. Its efficiency isn't brilliant, because the gases are very hot when they come out of the back. So we have lots of frictional entropic associated losses with this type of process. So what we could do, if we were being cunning, is to say, well, what I want is thrust. I don't necessarily want a small cross-sectional area of thrust with a very high momentum. I might be happy with a much larger cross-sectional area of thrust at a much lower temperature. So I'm getting more benefit, and I'm not throwing away a load of heat. So that's what we get in the lower example. And what we have with high bypass ratio engines is a great big fan that sits on the front of the engine, and most of the air that goes through the engine doesn't actually go through the combustion chamber. It goes across this fan, and of course this fan is driven by the core of the gas turbine, which is more analogous to the military engine. So that's the major difference between civil applications with a high bypass ratio, and we can see with this Trent 1000 here, the bypass ratio is about 11:1. So what we're saying is that 1 part in 11 of the total amount of air that goes through the front of the gas turbine actually goes through the combustion chamber and then across all the turbine stages, and 10 parts out of 11 don't go anywhere near the combustion process. They're actually being driven by the fan. So the fan itself is like a big propeller, really, that sits at the front of the engine. And we also have something called turboprop engines, which are essentially gas turbines with old-fashioned propellers on the front of them, and they're similar to these high bypass ratio civil engines. But what I'm trying to show you in this example is that some of the air doesn't go through the combustion chamber. It's actually being driven by the fans, which is giving thrust, but cold thrust, if you like. And that's the difference between the two engines. If you wanted a lot of energy from the engine, you wanted the aircraft to reach a high speed, and you weren't that concerned about efficiency, so you're quite happy to throw a lot of hot gas out the back without harvesting all of the thermal energy, then you'd go for a low bypass ratio design. If efficiency interests you and speed is not that critical, then you go for a high bypass ratio design, and hence we get. When we talk about power generation, then we're talking about gas turbines, which are static. So they're sitting on a frame, and they're being run very similarly to the propulsive applications, the jet engines you've seen in the previous slide, but they're just providing rotation. And there's a huge amount of systems like this in the world. So in the United Kingdom, 40% of all the electricity that's generated in this country comes from gas turbines. So these gas turbines would have also had their history, and you have to remember that the history of gas turbines is not that old. I mean, they were only really put into application in the 1950s. I know they were developed in the 1940s, but they were really crude, simple systems. In terms of power generation, this started pretty much in the 1950s. So we're not talking ancient history here. So the pedigree of these things we can trace. So the static generating systems came from one of two origins. The first were systems which were adapted. So originally gas turbines were there just for jet engine propulsion transport applications. And the engineers that were looking for possibly generating electricity from them said, well, why don't we take the existing designs that work? They're powered by liquid fuels, so we maybe change them to work on natural gas if we wanted to. Also, maybe we could put a bit of diesel in them rather than using something like kerosene. Let's adapt the designs we've got, not worry about the thrust, try and get more rotational power from them and generate electricity. So that's the first line. And you can see that example in a lot of systems. So in fact, Rolls-Royce, going back to the example on the previous slides, they developed a series of adapted, or they're known as aeroderivative engines. So the Avon is a good example of an aeroderivative design. And all the lessons which were learned in getting these things to fly were then applied for ground-based static electricity systems. So they were called the aeroderivatives. And then the second type of designs were designed almost from scratch, where the engineers said, well, we won't use the lessons gained from the aerospace sector. We will just design these things solely with the intention of having them as power generation systems. So they would be quite a different shape and size because their parent designs weren't originating from systems which needed to get shoved into engine nacelles and housed inside aircraft. So they would have looked quite different. But it's worth you knowing where these things would come from. The other major application of gas turbines would be in pumping liquids over extremely large distances. So the oil and the gas industry use these things to a huge extent. One of the reasons they use them is that they are incredibly reliable systems. You can run these things for thousands and thousands of hours without even having to worry about taking them for maintenance. And when I say run them for thousands of hours, I mean 24/7. So if you think of something like pumping oil or gas across Kazakhstan, for example, you've got massive open areas of prairie and of desert where you don't have the capability of having people manning these things. So you set these systems up to run all the time for months and months, and they are absolutely fine. They're extremely robust systems, so that's why we would tend to stick with gas turbines. Big power output, high reliability. You can house these things on oil rigs, on power generating sites, anywhere you want to pump things like oil and gas over vast distances. So it's a big market, not just in terms of electricity generation or propulsion, but also on large.
what we're going to do is we're going to look at the thermodynamics to a small extent during this lecture, and we will go on and understand it in much greater detail later on in the subsequent lecture. So what I want you to get out of this lecture is pretty much just the makeup of a gas turbine. So what we've got in front of us are process symbols for a typical process diagram in a gas turbine. What have we got? So on the left is the symbol for a compressor, and it's a trapezium, and you can see that one length is a lot longer than the other, so it's almost saying the gas is coming in, is being squashed. That's the purpose of a compressor. So the air flows into the compressor at station 1. It then gets squashed down to station 2. So if the compression ratio in a particular engine is something like 20 to 1, then what the term we use in gas turbines in the Brayton cycle is pressure ratio. So this isn't compression ratio like with the diesel or the Otto cycle. This is pressure ratio. So if it goes in at 1 bar and the pressure ratio is 20 to 1, then it exits the compressor at 20 bar. So we've squashed the gases down 20 bar, then they go into the heater, or the combustion chamber in our case. We normally just draw a box for that. As we know, the pressure doesn't change in the heater, so if it was 20 bar pressure ratio, we're still at 20 bar now. Out of the heater, extremely hot gases, and then we expand them in the turbine. So they go into the turbine and they get expanded. Normally, they get expanded back down to atmospheric pressure. The temperature drops across the turbine and we extract work. So remember that the turbine now feeds that work into the compressor, and that's what gives us our cycle. Now, the air flows out of the turbine and it goes, I guess theoretically, it goes into a cooler. It's not really a cooler, it's the Earth's atmosphere. So most cases, this is just the Earth's atmosphere. What we're doing is we're dumping the hot gases that have come out of the turbine. Remember, energy quality, that kind of thing. We can't extract all of the heat out of the turbine, so we extract as much as is practically possible, and then we just simply dump the rest. We sort of view the Earth's atmosphere as being an infinitely large cooler, and that's a pretty fair assumption to make. So then we pick air up from somewhere else, but that's okay to use this in our thermodynamic model. Now, there's one thing I certainly wanted to take away from this is the station numbers. So in the industry, the convention is almost always like this, okay? So 1 is always the inlet, 2 is always the exit of the compressor and the entrance to the combustion chamber. 3 is almost always the inlet to the turbine or the exit to the combustion chamber. So we talk about something called turbine inlet temperature. We almost always give that the number 3. And then the back end of the engine is almost always called 4. Okay. So when gas turbine engineers talk to each other, they will literally sometimes say, "Oh, what's your T3?" And they'll all know between each other that T3 means the turbine inlet temperature. And you'll see later on in this module that T3 is the most important part of gas turbine design, and it's the limiting factor. So make sure that you understand that process diagram, and that you could probably draw it from memory. It's not difficult, but I need to make sure that you understand this before we go any further. Let's take a look now. All right, so similar to how we did this for the diesel cycle, what we've got in front of us is the pressure volume diagram on the left. And then on the right, we've got the temperature entropy diagram. Now, when I'm teaching you the Brayton cycle, we're going to work almost exclusively with a temperature entropy diagram. In fact, this is the only time you're really going to see a pressure volume diagram for the Brayton cycle. However, it will perhaps help as a useful grounding for you to look at the pressure volume diagram at the same time. Okay, so let's do what might seem familiar to us. Let's go through the different parts. So the first thing is theoretically, we've got isentropic compression. So air flows into the compressor, it gets squashed, and whilst it's getting squashed, it's going to heat up, but we're not going to have any degradation of the energy itself as that happens, because what we're doing is we're assuming that the gases are going to behave themselves as they're squashed. In real life, that doesn't happen, but non-ideal behavior comes later on in the module. Okay, let's do that. Let's go into the first part of the cycle. There we go. I've put that in nice and slow so you can understand what's going on. If you want to have a look at the PV diagram, it should be a bit familiar to you because it's quite similar to, for example, the Otto or the diesel cycle. So the specific volume is going to go down because the gases are being squashed into a smaller and smaller passage, which is what the design of the engine looks like, and the pressure shoots up. Okay, let's have a look at the TS diagram. So in the TS diagram, the temperature of the gas is obviously going to increase. That should make some sense to us. And there's no real increase in entropy because we're just squashing the gases down. They're getting a lot closer together, and you can use the poor analogy of chaos in terms of entropy. But I just like to think of it as energy quality. So there's no real degradation or change in the energy quality because we're just squashing the gases down. All right. So now comes the interesting bit. We go into the combustion chamber. So fuel is added and combustion occurs at constant pressure, which we know. And the air is effectively just heated. So let's watch the traces on the two diagrams for that one. Okay, there we go. So in the PV diagram, constant pressure, an increase in specific volume of the gases because they're being heated. Okay, that makes sense to us. Let's look over on the TS diagram. So what we see is a substantial increase in temperature. That makes sense. We're burning jet fuel in air. Okay. And we see a huge increase in entropy because what we're doing is we're taking some fuel, which was nicely ordered. Its energy quality was very good, and we're degrading that energy quality by burning the fuel. So we see a huge increase in the entropy as that happens, and that's how the universe works. As we change chemical bonds into energy, the entropy will increase because the value of the energy is starting to degrade. But that's exactly what we want to do. We're handing energy down from a chemical potential energy into becoming thermal energy, which is what we wanted to do. So we see that increase on the TS diagram. All right. So now we've got isentropic expansion. We're going through the turbine. So we go through the turbine and we're going to see the temperature of the gases coming down. We won't see a change in entropy because we're assuming everything's going to be uniform and the quality of the energy will stay the same. So let's have a look at that part. There we go. Not unfamiliar to you in terms of the PV diagram. We're just moving down down a line of constant entropy there. So you'll see the pressure change and you'll see the volume change. That's fair enough. That's very similar to a four-stroke engine cycle. But if we look over on the TS diagram, we can see that we get this drop in temperature and no associated change in entropy. Later on in the module, we'll start looking and understanding what that actually means if it wasn't isentropic. Okay, we need to complete the cycle now. So let's move on. So you can see that the power output will be explained as the difference between the work done in the turbine and the work done in the compressor. So the energy that we get is going to be the difference between what the compressor's doing and what the turbine's doing. That should be fairly logical. And when it comes to expressing efficiency, which we'll do later on in the module, we'll take a look at that. Obviously, the work done in the turbine is negative with respect to what the work done in the compressor is negative with respect to what the turbine is doing because they're working in opposite directions. One is putting energy into the gas and one is taking energy out of the gas. Okay, so we've completed the cycle. We've used we've used the Earth's atmosphere as our infinite source of cooling, and you can see that we now complete the cycle between all 4 points. So this is the thing that we're going to look at in much more detail. I've just run through the basics of it for you here so that you can understand what's going on. So hopefully this should make sense to you now. It's in a lot of textbooks, so if I haven't made perfect sense, then just go have a look at this for yourself. So Thinking about the Brayton cycle, the ideal efficiency is always going to be a lot less than the Carnot efficiency, and these are the sort of things that we discuss in the lectures, isn't it? Is the Carnot efficiency is based simply on differences in temperature between energy sources at different temperature points. That's fine, but it's ideal. It doesn't work in practice. The Brayton cycle is much more interesting than the Carnot cycle because it actually works in practice. The Brayton cycle is what is used on modern gas turbines, modern jet engines, because there's direct work extraction. It's not just a simple theoretical process where this imaginary heat engine works between two different temperatures. So heat isn't transferred at a constant temperature during these constant pressure processes. The heat is transferred over a range of temperature scales, so we're going to get different interactions and different energy qualities as we start to change the temperature. The work done in compressing the air, so we have to compress the air. Where do we get that energy from? Well, we get it from the turbine. So it's quite large. It's comparable to the turbine work. So they're not huge a distance away from each other. So because the two are comparable, what that's telling us is that we're not going to get brilliant efficiencies from this cycle. However, on a practical basis, the efficiencies are quite high if you compare it to, say, the real application of a reciprocating engine. So the work ratio will actually be quite a lot less than 1, but that's okay because in a real scenario, we actually get quite a lot of work out of these engines. They don't work on a wonderfully theoretical basis like the Carnot cycle. They're practical systems. So although the numbers don't look great, when they perform in real life, they're actually very, very good. They're extremely efficient. So work ratio would simply be the energy between what the turbine's doing and what the compressor's doing, which we can see by the formula there. All right, so the efficiency of a simple gas turbine is quite low compared to, say, something like a steam cycle. And there's also a lot of irreversibilities in here, so we do actually get a lot of let's say a lot of noise. Well, I mean, the video is pretty much a testament to that, aren't they? So you're throwing a lot of energy out the back of the system when at very high speeds. Now there's a great irony in this is if we're looking at jet propulsion, that's exactly what we want to do. We want to throw all that energy out at high speed, but that's really hot gases that are going to waste. What we'd like to do from a thermodynamic textbook point of view is we'd like to throw the energy out of that engine at a very low speed, at a very low relative temperature, and harness as much energy from the gas as possible. But that's not going to give you very good thrust. Is in the same way for a reciprocating engine, what we want the piston to do is expand really slowly, but we know we're not going to get a lot of speed out of that or a lot of RPMs out of that. So almost in a very analogous way in the Brayton cycle, we're going to have a lot of irreversibilities because what we'd like to do is throw hot air out the back of the engine as fast as possible. But in reality, that works very well, but on a theoretical basis, we wouldn't want to do that. So then you start realizing why we have high bypass ratios. So we're harnessing more and more energy out of the turbine in order to drive a big fan. But one of the great advantages of the gas turbine and the Brayton cycle is that the fuel is burnt directly in the air. So you don't have all the associated issues with steam systems, as we're going to see later on in the module. You would never build a steam-powered aircraft, and I'm sure you could think of 100 reasons why a steam-powered aircraft would be a stupid idea. The advantage of a gas turbine is that the fuel and the air are in direct contact, so the system is relatively more straightforward and a hell of a lot lighter, which is why we use these particular systems. So on paper, the Brayton cycle doesn't look good, but in real practicality, it's probably one of the best options for things like propulsion or large-scale gas-fired power generation. Relatively speaking, the plant is exceptionally compact, and it's I'm going to be careful with the word cheap or cost effective, but they can be a lot more cost effective than things like steam plants, but that's That's all relative. One of the key things is they are extremely compact, and when you see pictures of gas-fired power generation systems, you realise how small these things are compared to their steam equivalents. So this is very important for aircraft and things like peak loading equipment, where we are, and again, the word cheap is a bit of a misnomer there, but when we want to quite quickly get power into the grid, and we want to get up to speed quite quickly. Gas turbines are a bit more flexible in that respect. Gas turbines are going to have to play a role in the future, keeping up with the inherent changeability of renewables. So if the sun stops shining or the wind stops blowing, but we still need power and we need engines to come up to speed quite quickly, gas turbines are probably a more viable option than things like coal-fired steam power generation. There's a lot of relativity in what I've just said there, but gas turbines tend to be the preferred option for grid balancing with renewables. All right, so we've pretty much finished this lecture. I want you to make sure you understand it all before we go and do the actual teaching session in the timetabled slot. We've looked at the principle of gas turbines, so what I want you to understand at the very minimum is just how does a jet engine work? If you can get that, then there's lots of things we can discuss. Jet engines are used for propulsion, but they're used quite substantially in the UK for power generation as well. So I need you to understand those cycle diagrams. We're going to talk about those in the lecture, not so much the PV diagram. You'll probably never have to deal with the PV diagram at all for gas turbines after this. Make sure you can draw it. It's not that different to some of the reciprocating engine cycle diagrams we've seen. There's some similarities. It's the TS diagram I need you to understand, and understand the significance of it, and what the area enclosed by the that shape is, that sort of thing. So what we'll do in the next lecture is we'll look at the theoretical efficiencies, and we'll calculate theoretical efficiencies before we go on and look at modified cycles and what their new efficiencies might be.